Great. Okay.
Okay.
Would you like the full screen mode again?
No, I want to keep it like
Okay,
this, actually, because
okay.
I'm going to have to go back and forth
Okay.
to the desktop. All right. So what I want to do is delve a little bit more deeply into the Bayesian computation issue, and then we'll see how this works. I have some R documents written in R Markdown that'll give you an example of these things, and it's on the desktop. You guys can keep it and distribute it. It's not a problem, and we'll see if this makes any sense. So we'll see if this works. Okay, so I want to talk about Bayesian computation. As I just said, I'm going to show you at least 2 examples, and a third if we have time. Simple Bayesian regression, hierarchical modeling, and factor analysis. Now, once you see how this is done in the simplest case, you pretty much have it. There's not going to be much difference other than one's ability to program into the software language the actual models you're interested in. But the general setup and the general ideas are basically the same. So let's see what we can do. All right, so as I mentioned toward the end of the last discussion, last lecture, that the idea behind Bayesian computation is that when you look at the expressions for these posterior distributions, which if you remember from the previous slides, you're literally multiplying 2 distributions together. So these have really complex expressions. It's not just P of Y, there's something. There's the expression for the normal distribution, it's math. And what you're doing is you're taking that distribution and you're multiplying it by another distribution so that what you end up with is a very complex expression. And even in the simplest case of just multiplying 2 normal distributions together, it takes a little bit more time than usual to try to actually get results from something like that. So the idea is to instead of trying to analytically solve for the estimates of a posterior distribution, we're going to draw samples from that posterior distribution and then summarize the distribution formed by those samples, and that's called Markov integration, Monte Carlo integration. So Bayesian inference focuses on estimating the features of this posterior distribution. You can get the mean, you can get the mode, standard deviation, and as I mentioned, the intervals or any kinds of intervals you want. And you can read them directly off of the posterior distribution. So now, what's the basic idea? MCMC starts by drawing samples from the parameters of interest from the posterior distribution, P of theta given Y, and then approximates this by taking 1 over the number of samples times the sum of each of the probabilities of each of those samples, from the probability distribution of those samples, and that's a mean. So what I was trying to point out earlier is that this is a rather simple expression, but from a very complex posterior distribution. Now, if we assume that the samples are independent of one another, and that's going to be important, we're going to return to that. If we assume the samples are independent of one another, then the law of large numbers ensures that the approximation here will be increasingly accurate as t increases. T is the number of samples drawn from the posterior distribution. It's like the sample size. And that is under our control as a user of the software. Now, the samples do not have to be drawn independently, at least not at first. But all that is required is that the sequence of draws result in samples throughout what we call the support of the distribution. In other words, as you're drawing samples from this posterior distribution, if it helps, in fact, I think if you don't mind, I'm going to just waste more of your paper. For now, let's see. Okay, for now, I want to draw a normal distribution because it's pretty much the only distribution I know how to draw. And we're going to assume that that's the posterior distribution, the theoretical posterior distribution. And then what I'm going to be doing is sampling large number of draws from this posterior distribution, and they're all going to get accumulated down here on the bottom and form a nice posterior distribution as the sample size, in this case t, increases. What I mean by the support of the distribution is that what's going to happen is that MCMC is going to start by first taking some random number and then drawing that value out. And then it's going to do it again, but it's going to take the second draw, let's say it's over here, partly dependent on that first draw, which is called a Markov chain. There's where the MC of MCFC comes in. It's going to take this Markov chain. Now what you want is you want the correlations between these lagged correlations to go away pretty quickly. And in particular what you want is you want to make sure that the entire distribution is sampled from. That it's not somehow accidentally locked into one corner of the distribution. So taking large numbers of samples helps. And then also ensuring that the Markov property disappears pretty quickly. Now the beautiful thing about this is, as you'll see, is we're going to have lots of diagnostic statistics to look at to help us come to the conclusion as to whether or not this thing has converged to the posterior distribution, theoretical posterior distribution. In doing Bayesian statistics, from a practical point of view, the diagnostic measures become absolutely crucial, completely crucial. You cannot move forward unless you feel very convinced that things have stabilized. So the Markov chain allows sampling through the support of the entire posterior distribution while also relaxing the assumption that it's independent sampling, though often independence happens very quickly, as you will see momentarily. So formally, a Markov chain is a sequence of dependent random variables such that the conditional probability of a particular random variable theta s given all of the past variables depends only on the previous one, and that is only on the immediate past variable. And this conditional probability is referred to a transition kernel of the Markov chain. That's a little technical, but there you have it. Now, the Markov chain has a number of important properties. These properties are crucial, and we have the diagnostics to understand them. And I basically stated one just a moment ago. Over a long sequence, the chain will forget its initial state and converge to the stationary distribution, which does not depend either on the number of samples that you take nor on the initial state of the parameter itself. The number of iterations prior to the stability of the distribution is referred to as the burn-in. And that's because what happens is as it begins a process, it's going to basically fluctuate in a lot of very dramatic ways. And you don't want those initial chains to be part of your overall inference because it hasn't stabilized yet. So what we're going to do is we're going to allow the Markov algorithm, the MCMC algorithm, to basically bounce around for a while until it stabilizes. Then we're going to cut those out of the inference. And that portion we're cutting out is called the burn-in. Once those are gone, everything then depends, your inferences then depend on what has been stabilized after that point. And you'll see pictures of all this in a moment. So yeah, the number of iterations prior to the stability of the distribution is referred to the post-burn-in, or is referred to the burn-in, and then the post-burn-in is used to determine this thing called an ergodic average, which is now the average of the estimate we want of that probability distribution, like the mean, which is now the number of iterations minus the burn-in. So we're basically discarding the burn-in. Now, I'm going to probably run back and forth to this board, so I hope I don't drive you completely crazy there. But to continue with the chains, because this is what we're talking about now for the next hour and a half or so with regard to the chains, a decision has to be made regarding the number of chains that we're going to generate, as well as the number of iterations, t, that we're interested in. Each chain can start from a different position of the posterior distribution. So for example, I can tell the MCMC algorithm, I want you to just start taking one chain of iterations out of this posterior distribution. So it starts here, starts taking out drops from this posterior. The problem is it could very well get caught in there and not traverse the support of this posterior distribution. You don't want that. So what you can do is you can tell the software that you want it to pull out multiple chains by starting another random seed somewhere else in the distribution over there. Now it's going to start pulling out t iterations of this chain, but from another part of the distribution. With enough of these iterations, all of this will just converge very nicely, we hope, into the posterior distribution. And we have diagnostics to check for that as well, which you'll see. So we're heading there. So a decision must be made with regard to the number of Markov chains, as well as the number of iterations. Each chain samples from another location of the posterior distribution based on some random starting values that the computer decides on. With multiple chains, it may be that you don't need as many iterations because you're doing these iterations to get the support of the posterior, but you might not need to if you have lots of chains. In some cases, the same result can be obtained from one chain, although you might need considerably more iterations to handle this. Once the chain has stabilized, the burn-in samples are discarded, then we can get our summary statistics, the posterior intervals, the mode, the median, the mean, and so on. So we're all set to go. Now it's going to be crucial, as I already mentioned, to determine whether or not these things have converged. These are computationally extremely intensive, very intensive. And the really, really bad news, this is the point in the talk where people get up and leave. The really bad news here is that it can take an awfully long time to run, okay? Depending on the sample size of your actual data, depending on the complexity of the model. And the hard part of this is that this will run for a very, very long time, and then you'll find out it didn't converge. And then you have to start over again and run it again. And so this can be a rather frustrating thing. Now, having said that, this is a computational problem, and there will be a computational fix, and people are already working on speeding this thing up. And if you have access to high throughput computing, high speed computing, that certainly helps as well. Not everybody has that access. Yeah?
Just to clarify,
sure.
You said that you can start over and again try. So eventually you assume that it should converge at some point. If you have enough computer power, you will get there at some point.
Well, there's a data prior combination here. And so consequently, I mean, it may take a lot of tweaking, a lot of fine tuning in order to be able to get it to converge. Yeah, if that's where the problem is coming from. But remember, the problem can come from two places now, right? It can come from the model and the data. Excuse me, the data and the prior.
So it's possible that you'll never.
It'd be very hard, or you'd give up. Mm-hmm. I mean, for practical purposes, you probably could very well give up. So we're going to look at 4 diagnostics, so there are more than this. These are the key ones. Something called the trace plot, something is also called the history plot, the autocorrelation function plot, the Galecki Diagnostic, and the Gelman-Rubens-Brooks Diagnostic, which we'll talk about in practice in just a moment. The program I want to introduce you to, but it's by no means the only program out there, is a program called JAGS. JAGS stands for Just Another Gibbs Sampler, and it has an R interface, so you get all the benefits of R at the front end and all the benefits of R at the back end with JAGS in the middle. There's a lot of these R things now. There's RStan, RM+. There's a lot of these various wrappers, I think is what they call them, wrappers of these things. JAGS is what we would refer to as Bugs-like. Bugs was the first package to ever do this stuff, which made its way into our world through WinBugs. Bugs stands for Bayes under Gibbs sampling. And Bugs, as I said, was part of within WinBugs. WinBugs is not supported anymore. And so there's an open source version called OpenBugs. If you already know Bugs, then you know JAGS. So that might be helpful to you. There's not going to be anything really new here. If you don't, JAGS is fantastic. And Stan is kind of Bugs-like, but it's a little bit different. So the JAGS is a very good package to start somebody on if they want to do their own kind of programming within Bayes. So what are the steps of our JAGS? Well, you bring in the data and you use R to do any of the manipulations you would like to do. For example, handling missing data, getting all of your nice plots, descriptive statistics, the usual general thing that you might do. You do that in R. Then what's going to happen is you're going to write a model using the JAGS language and save it in a file called a .bug file. The data and the model get passed to JAGS using the jags.model command, and then another program called CODA does the actual MCMC analysis, and then you run this back out to R and get the plots. So I have a file which you will now have once it's all given to you. I hope I can find it. Where did it go? That's not it. Oh, that's me. Well, that's interesting. I'm looking for my I'm looking for the desktop. There's the desktop. Is that the desktop?
Yeah.
And there is is that the material? Great. And here is the first thing I want to show you. This is going to be the simple,
Just click start. Yeah, start Firefox.
start Firefox. That's right, it's an HTML file, Firefox. Okay. Let's hope this works. There it is. Can you see this? Can you see it? I'm not sure how much I can zoom it from here. By the way, this is stuff I'm actually doing in my Bayesian class right now. I'm just giving it to you. Okay, I don't know how much you know about R. This is not an R tutorial, but it's a JAGS tutorial. So I'm going to assume that you know R, or that you know somebody that knows R, a friend, a relative, something like that you can talk to about this. But what I'm going to do is I'm going to download. First of all, I have to actually download JAGS. So you have to get the JAGS program, and you can get that in a computer, in a repository called SourceForge. But if you just Google JAGS and make sure that it was software program, you can get to it and download it pretty easily. Then you would install and require RJAGS. Now, what I'm going to do for this particular simple example is I'm going to generate some fake data. I'm not going to do regression yet. I'm going to take you one step at a time through this. I'm going to generate some fake data of a sample size of 100. Then I'm going to generate Y as a random normal variable with sample size 100, mean of 0, standard deviation of 5. That's it. There's R. Now I go to JAGS. So this piece right here was just R. In JAGS, what one does is starts with the name of a particular program you want to call it. I'm going to call it model string. What you might not be able to see here, but you have to be careful of, is that there's an equal sign and then there's a quote mark, double quote mark. As you know with R, and it's the same with JAGS, R is very unforgiving about syntax issues, so same with JAGS. So now I want you to see what I'm doing here. I now have a code that starts with the word model. I have an open bracket, and I say, for I equals 1 to n, where n was defined as 100 up here, I want each person's observation to be generated from a normal distribution with a mean mu and a precision tau. And notice what I said, that's very important. When you are now within the JAGS code, JAGS doesn't talk about variance, it talks about precision, and I forget this every time, but it talks about precision. Remember, precision is 1 over the variance, so you just have to keep that in mind. Now, this part here, if you were in the previous lecture, this little part right here, that's the likelihood. That's P of Y given theta. Right there. There's Y, there's the probability model, and there are the parameters. Now, I'm done with the likelihood. Now what I'm going to do is put priors on my model parameters, because I'm a Bayesian, and I'm going to put models on my model parameters. So I have to put a prior on the mean, mu. I'm going to assume that the mean, mu, is normally distributed, and it too has parameters, which we call hyperparameters in the Bayesian literature. And I'm going to assume that the mean is 0, and the precision is very low. That's not a variance, that's precision. So the precision is 0.0001. Very low precision, meaning very high variance. I'm being non-informative here. This is a very, what we would call a vague prior. It's a very vague prior. Now I have to put a prior on my precision term. Remember, every parameter requires a prior. So I have to put a prior on the precision term as well. Now, if you get deeply into Bayesian statistics, you learn a lot about distributions that you might never have actually heard before unless you took a good probability in statistics class. For example, precisions can have what are called gamma distributions. It's a distribution you might not have heard of, but anyway, that's the distribution of a precision, is the gamma distribution. These two hyperparameters are called the shape and the scale of the gamma distribution, and I'm making these relatively non-informative as well. Then I'm going to do something else that I can do as a Bayesian. I am going to calculate the standard deviation because maybe I don't want to talk about precision. Maybe I'd like to get the posterior distributions of the standard deviations of this distribution. So I can do that by doing a transformation and defining the standard deviation as 1 over the square root of the precision, which is the standard deviation. And that's it. So there's my priors, and there's the end of the loop, if you will, and there's the end of the JAGS code. Now, I end the JAGS code and I go back to R. And these lines here write the line out to this bug program. It defines my variable list, y is y and n is n. I give names to my parameters, and then I'm going to write a new object. I'm going to call it simple mod because this is a simple model. It's a jags.model. It's going to read in the bug file. It's going to read in the data. I'm going to ask for 2 chains. And then this thing here is what are called adaptation steps. I'm not entirely sure I understand what the adaptation steps do either, but it's, again, an issue with the algorithm of trying to tune it and stabilize it even before it begins its burn-in. These numbers, by the way, the number of chains and the number of adaptation steps I've chosen. And I've chosen two chains here. Then you get some stuff that comes back from the code. This line here is just going to allow me to monitor the burn-in. I can just watch it as it's going. This here is the burn-in stage. So I write a command called update using simple mod, and the number of burn-in iterations is 5,000. Now, this line here is the continuation of the post burn-in. The burn-in will be lobbed off eventually, but these are the post burn-in. I will then see this, the program tell me that it's going through the chain. And then finally, I have something I'm going to just call coda samples 1. And I'm going to, which you can call it anything you want. I'm calling it coda samples 1. I'm going to call in a program called coda samples. It's going to use simple mod. It's going to read in my variable names. And then here are the number of post burn-in iterations. 100,000. 100, that's T. 100,000 post burn-in iterations are being called for here. But for purposes of storage and plotting, I'm only going to have it pick every 10th draw. That's called the thinning interval. That becomes useful. That can become useful. And then here's a starting seed just to get the whole thing rolling. It's a pretty bad seed, by the way. You wouldn't want to give it the same number, but that's what I did. Now, the plots are not all that great on this particular R Markdown language, but it gives you an idea of what's happening. So now I'm going to use Coda to obtain diagnostics. And the first set of diagnostics I want to look at are the thinning, is a trace plot. Now, a trace plot is a plot of the post-burn-in iterations as it's going across the number of iterations. And what you're looking for pretty much is what you're seeing right here. A beautiful kind of caterpillar plot that goes across the number of iterations with no clear disparities, that it really looks nice and clear. But aligned with that is something that is really important to look at. There is the posterior distribution of the mean. Not the theoretical one. This is the posterior distribution of the mean. This is 10,000 draws plotted. The density plot of 10,000 draws of the posterior distribution. Now, it should have this nice bell shape to it because the posterior distribution of a mean of a normal distribution should be normal. And it looks pretty normal, but it is actually, if you look at it really carefully, ever so slightly lumpy, right? So in fact, even with 10,000 iterations and a really simple model, this isn't absolutely as smooth as it possibly could be, but it's probably close enough for government work. So now, if you take a look at the, just want to see if you guys got that. If you look at this red plot now, you'll see that actually it is a little spiky in certain spots, indicating that it's kind of flying off, not really beautifully across, but it's okay. You will also notice, if you can see it on the screen, that there's red and there's black. Those are the two chains. And we're not seeing one chain diverge far from another. All right, this is the posterior distribution of the standard deviation. Standard deviations can't be negative, and so we see this thing hovering right around whatever its true value is, and here's the posterior distribution. Similarly, with the precision parameter, we're getting its posterior distribution. So on the basis of this set of diagnostic plots, one might feel fairly comfortable that it's converged. But it's not the only thing we want to look at. Next thing we want to look at.
Excuse me.
Yeah.
Sorry, may I interrupt? So tau and sigma are analytically, mathematically related.
Yeah.
They express the same kind of information.
Yeah.
But what RGX does here is it estimates them separately. Or why is it that we're getting an independent plot?
I can get posterior distributions for any parameter I wish, including functions of parameters. I just ask for it. So they are definitely related to each other, but it's just for each draw of the posterior distribution, it's calculating the standard deviation from that as well, and then calculating over the draws. Does that make sense? You can ask for any function. If you're doing structural equation modeling, you can get indirect effects and the posterior distribution of indirect effects.
The more parameters I ask for, even if they're just mathematically dependent on something that I really want to get from my model, it means that there's more computations.
Oh yeah, that's true. Yeah, that's true. You may not want to do this. I was just showing.
Okay.
I was just showing you that you could, but no, you're absolutely right. That's just going to take more time. Now this plot here is the plot having to do with. Oh yes, I'm sorry. Yeah, please.
Could you show the arc for where's the burn-in stage again?
Up here, it is right there. That's the burn-in, 5,000 burn-in.
And how did you decide on the 5,000?
I just made up the number.
So it's no problem if that's too long, right?
You wouldn't want it terribly long, but you wouldn't want it terribly short either, and that may take some time and practice. In other words, it's very problem dependent. To my knowledge, I don't know of any rules of thumb that say, well, if you're going to have 100,000 iterations, you should have 1/5 of that or something of that sort. I'm not aware of that. I would say that you certainly, the more iterations that you're going to have, the more burn-in you should have. But what the ratio of that number is, I don't think is really dependent, because these things also are related to the number of parameters and the complexity of the model. If you saw some problems with this trace plot here, or actually, more importantly, this one, and you'll see them in a few minutes actually. This one here happens to look really good, but I'll show you later ones that don't look all that good. That may be the sign that you need more burn-in time.
But if it's too long, it's not a problem, right? We just lose.
Yeah, M+, for example, takes 50%, just as a rule. That's the default. 50% of the total number of iterations are devoted to burn-in. I think that's a lot, but
I thought that when you define burn-in, I thought there was some internal criterion by which you decide, okay, it's stabilized, now we start.
No, there's these ad hoc criteria. There's a sign that it's stabilized. It's not the only sign, but it's a sign that it's stabilized. You would actually know it if it didn't. And in fact, I believe it's the case that JAGS will allow you, let me just double check something for a second. Where'd it go? Oh, I just saw it. Oh, here. I think that you can add a line here, add a command here, that allows you to see the burn-in iterations as well. In fact, I should have done that, and I apologize, but I think you could actually see the burn-in lines as well. That way you know whether it is in fact moving to that and where that stopping point is happening. You can see, yeah, you can actually see it kind of going toward that, yeah. This problem are just too simple, but I didn't do this. So this thing here is showing the autocorrelation issue. So if you remember, I said that the second draw is dependent upon the first and so on, and that while those are dependent samples, you would like those dependency to go away. One way to do that is to plot the autocorrelations among the draws and see if those autocorrelations vanish quickly or not. So this is an autocorrelation plot, And you'll notice that the autocorrelation, maybe again hard to see, the autocorrelation of the second draw with the first is 1.0. But the autocorrelation of the second draw with the first, or third draw with the first, is 0. So the autocorrelation has gone to independence extremely quickly. This is a good sign. This is the ideal that you would want to see, is an ACF plot that looks like that. Now, actually, if you really look very, very closely at this ACF plot, those autocorrelations down there are not 0. So there actually is, even there, small dependencies. But they're so small that it doesn't make any difference. So I have 2 diagnostics to look at. And so far, everything looks pretty good. The third is the Gelman Diagnostic, or the Gelman plot. And there will be a Gelman numbers that will come up in a moment that you'll see that I like even better than the plot. The Gelman plot is actually really quite interesting. It's asking the question, is this red bar really on top of this black bar or not? I mean, the eyeball says it is, but the question is statistically, are they the same? And the way that it does this is it treats it kind of like an analysis of variance. It says, is the between-chain variation equal to the within-chain variation? And if that's the case, then the ratio should be 1.0. If the between-chain variation is the same as the within-chain variation, then the value should be 1. And that's called the potential scale reduction factor, the PSRF. And what you want, forget the red line, what you want is you want that black line to be as close to 1.0 as possible as it's going across the number of iterations. And it's doing this, it'll do this for, it's a statistic that you can only get if you have 2 or more chains, because it's looking at the ratio of those variations. So now what this is saying is that while the eyeball tells us that the black chain and the red chain are basically on top of one another, we have evidence statistically from the PSRF that these 2 chains are absolutely overlapping. That's good news. So far, we have the diagnostics of the trace plot, the ACF plot, the Gelman Diagnostic, all telling us pretty good news about this analysis. Now, this piece here is the Galecki Diagnostic. There is a Galecki plot, but it just doesn't work as nicely as the diagnostic. The Galecki Diagnostic is really quite interesting as well. What it's going to do is it's going to say, this thing looks like it's going straight across the screen, right? Is it, or is it not? And so the way that it does this is it says, I'm going to use the observations from the first 10%, the parameters from the first 10% of the chain, and I'm going to calculate a mean and a standard deviation. Then I'm going to take the observations from the last 50% of the chain, calculate a mean and a standard deviation from that as well, and then I'm going to calculate a z-test to look at whether the first 10% of the chain is statistically significantly different from the last 50% of the chain. And if that's the case, if it's not the case, if I can't reject the null, then basically it's saying the chain is actually going straight across the screen. It's not kind of going up or wiggling around, which it can for really complex models. So what I'm looking for here, in terms of the first chain, what I'm looking for here is z values that are greater than 2.0 or 1.96 in absolute value, which would suggest that there's something wrong. And here too. And what I see in both chains is that the z values for both chains are less than 1.96, and therefore the chains are converging in terms of this Galecki diagnostic. So my 4 diagnostics lead me to believe that everything's converged very nicely, and I'm going to proceed to interpret the results. In this case, there's nothing much to interpret because I'm just generating data from a normal distribution. But there's the posterior mean. It's 0.15, not 0. It's 0.15. Why is that the case? Sample size. The sample size is 100. Sample size is not like 10,000 or 10 million. If you went and did this again and had the sample size up to like about 10 million, or even larger than that, then this means it's going to be close to 0. But right now it's not. So you're seeing the relationship between a prior and this posterior. Here is the standard deviation, which was generated to be 5. It's a little bit more than 5. And there's the precision. This is the mean of the posterior distribution. These are the expected a posteriori, the EAP estimates. This is the standard deviation of the posterior distribution. This thing here is called the naive standard error, because they couldn't help themselves. And so what they did is they took the standard deviation and divided by the square root of the number of iterations. This thing here next to it is something called the time series standard error. These two together make for another kind of interesting diagnostic. The time series standard error takes into account the autocorrelation, whereas the naive standard error does not. But if there's no autocorrelation, then these two numbers should be very, very close to the same, which they are. And we saw that there was no autocorrelation from our autocorrelation plot. So it's just kind of confirming what we see. But it's another number to look at. And there are your credible intervals, the 95% credible intervals, which JAGs will allow you, R will allow you to change. So here, the true value, there's a 95% probability that the true value is between minus 0.86 and 1.21. So 0 is a credible true value with a 95% probability, and in fact, that is the true value. I generated the data that way. All right. So let's go back. So that was the simplest example of a JAGS program that I could basically show you. So let's get more complicated. We're going to talk about model building now. So now we're going to move up to regression analysis so you can see what JAGS looks like. In this context, things are going to be a little bit trickier now. Not much. The basic ideas are exactly the same. We have to write a likelihood, which is going to be our model, and then we have to put parameters on all of priors on all the parameters in the model. So the frequentist goals of model building and Bayesian goals of model building are the same. We've talked about this, I think. We are going to specify a model based on prior knowledge. We're going to estimate and fit the parameters of the model and the model itself. We're going to evaluate the model and modify it possibly, and then we're going to choose among the competing models. And we talked about the important differences in the earlier talk, so I think I'll pass those and go right to this issue of how we, in fact, evaluate the model's fit from a Bayesian point of view. So, as I had mentioned in the earlier talk, an important aspect of Bayesian statistical modeling is that the notion of what constitutes a well-fitting model, or a model that you would choose, is based on the notion of prediction. So the idea here is you're actually going to use the model for something, and what you would like it to do is predict what actually happened. Okay, so the idea, but in the Bayesian sense, this is going to have to be posterior prediction because it's going to have to include information about our uncertainty through the priors. So a natural way of evaluating the quality of a model is to examine how well the model fits actual data. This is true if you're a frequentist or otherwise. What we're going to do in the Bayesian approach is we're going to look at model fit from the notion of what's called a posterior predictive check, and then accompanying this posterior predictive check is something unfortunately referred to as the predictive p-value, the posterior predictive p-value. The general idea behind the posterior predictive check is that there should be little discrepancy between the data generated by the model and the actual data itself. It's what we mean by discrepancy. And it's true from a frequentist point of view as well as a Bayesian point of view. Posterior predictive checking is a method for assessing the specification quality of the model, but that any deviation now implies model misspecification that can be both in your priors as well as in the model itself. So things have gotten a little more complicated. And I'll give you an idea of how posterior predictive checking works so you get an intuitive idea of what's happening. To do a posterior predictive check requires that we calculate something called the posterior predictive distribution of replicated data. So imagine that we have a model, and now what we're going to do is try to reproduce the data from that model. We have the data in one hand, and we have data reproduced by the model in another, and what we want to know is the discrepancy between the two. So we're going to call yrep the data replicated from our model, and this is the formula for the posterior predictive distribution, and I think it's helpful to go from right to left. what we do is we start with a prior distribution reflecting our uncertainty regarding the model parameters. We then confront our prior uncertainty about model parameters with the actual data model that we have in our hands. It's regression or whatever we want to do. P of y given theta times P of theta is the posterior distribution. So there's Bayes' theorem right there. P of theta given y is P of y given theta times P of theta. Now, once we have calculated the product of these two and gotten our posterior distribution, I'm going to go back up to this slide. I'm going to take those estimates, and for each estimate that I get from the MCMC, I'm going to generate replicated data from that. Then what I'm going to do is integrate out the parameters of the model, and I will end up with the probability distribution of the replicated data given the observed data. I'm going to get this discrepancy probability is what I'm going to get. And that's called the posterior predictive distribution. And it shows up in Bayes a lot, in particular in missing data problems. Yeah?
Just to clarify, how is it different from regression where we have predictive values?
The difference is, exactly. The difference is that it's in the posterior. So this is picking up uncertainty in the parameters. Otherwise, it's very similar. Now, okay, so I just basically defined that. I don't think that I need to go over what this is again. But to assess the model fit, just as you pointed out, means checking whether the replicated data matches the observed data. And if it does quite well, then we say that the model fits the data. But how are we going to do that? Well, one approach, the approach that we use, is something called a Bayesian p-value. Now, the idea here is first what we have to do is define what we mean by discrepancy. Okay? And that could be any measure of discrepancy you happen to like. So it could be a chi-square measure of discrepancy. It could be mean absolute deviation measure of discrepancy. It could be any measure of discrepancy you like. I'm going to come back to that in a moment because that's really important for this. So I'm going to denote a statistic. I'm going to call it T of y, and that statistic will be, for example, the chi-square. Chi-square is a nice measure of discrepancy, so I'm going to use that one. Or I can use residual fit. Like in regular regression, I can use residuals. And so this statistic, T of y, is based on the data. But now what I'm going to do is I'm going to calculate a T of y for every replicated, for the replicated data from each draw from that posterior distribution. So I'm going to have 10,000 chi-squares, let's say, or 100,000 chi-squares. And I'm going to compare each one of them to the chi-square obtained from the actual data itself. And I'm just going to count the number of them that are different. Right? The p-value then is the proportion, so think of PR more as a proportion, of the test statistics based on replicated data under those parameters greater than or equal to the actual chi-square based on the data itself. And I'm just going to count them. So what I'm doing is I'm accounting for uncertainty through the posterior distribution and the posterior predictive distribution, which is then being picked up by this chi-square in this particular case. Now, if the model fits the data perfectly, or very well, let's say, if the model fits the data very well, these chi-squares should just bounce around randomly above or below the actual chi-square from the data. Just random variation. Meaning that the magic p-value number that you want here is 0.5. Not 0.05. Don't make that mistake. I know it's a p-value, but 0.5. 0.5. Now, M+, just as a forewarning, M+ rescales this posterior predictive p-value so that 0 is bad and 1 is good. Okay, so just keep that in mind. It's the same basic idea, but just keep that in mind. But if you're using JAGs, it's going to be 0.5. That's how it's set up, unless you want to do your own rescaling. It's going to be 0.5. And all 0.5 means is that the chi-squares that you're getting from the replications of this MCMC process are bouncing around just randomly from the chi-square of the model itself. And that's a good sign. If it's not, if it's much greater than 0.5 or much less than 0.5, depending on how you set it up with the sign, then it's suggesting model misfit, which can be occurring anywhere. It could be in your priors, or it could be in your model, or both. Okay, and we'll see the PPP in just a moment. So that's the posterior predictive check. I want to come back very briefly to this issue about how powerful this posterior predictive distribution is, and in particular, the choice of this test statistic. This is a kind of a global measure of fit. The chi-square is a global measure of fit. In regression, as you'll see, I'm just looking at whether the distribution of the residuals are normal. The usual kind of goodness of fit statistic that you might want to look at, you can certainly do with ease. But that might not be the only thing you want to do to diagnose fit of a model. Depending on your needs, you may be interested in whether or not the model is capturing extreme values or outliers well. In other words, this test statistic doesn't have to be some overall global measure of fit. It could be some localized measure of fit that you're mostly concerned with. Like, you don't care whether you got the bulk of the observations, you just want to know whether your model detects outliers. So if you have a good model, and the model is supposed to detect outliers, then you are not going to necessarily ask for a global measure of fit. You can construct whatever measure of fit or diagnosis you want, because it's going to come out of this Markov chain each time it's calculated. And all you're doing is calculating the discrepancy between each one of those indices, whichever one you want, against the one that was calculated for the data. So that bad fit here might mean a model that can't find outliers. Or a model, I can't even come up with them because we usually don't do this in the social sciences, but this allows for a much greater tailoring of the kind of diagnosis you want to do with regard to fit. Fit does not have to be omnibus overall fit. That might not be interesting. That might not be the point. It usually is for us. It usually is, but it doesn't have to be, is the point I'm trying to make. So if you're clever enough, you can create your posterior predictive checks around anything you wish to create. Again, in M+, and it's been years since I've touched M+, so I actually don't know. But I think in M+, it's the likelihood ratio chi-square that it's calculating, I think, for the PPP. And I think it gives you another choice maybe, but that's about it. Which is understandable, because in the SEM context, we're typically interested in overall fit. So I get it, but it's not, not the only thing. So we're drilling down. We're going to get close to regression in a moment. This is how we would assess the overall fit of the regression analysis. Posterior predictive checking is what it's called. Gelman's done a lot of work on this topic. The next phase, which I alluded to, but I'm going to talk about in a little bit more detail now, is that when we build models, especially structural equation models, it's often the case that we will mess with them. We'll add paths, take away paths, or add variables and take away variables, but eventually settle on something. And the question would be, how do we adjudicate among the competing models that we're interested in so that we can choose one and then get on with the results? Well, a very simple approach for this problem of model selection is based on something called the Bayes factor. The idea here, as I mentioned in the earlier lecture, is to quantify the odds that the data favor one hypothesis over another, and that these models actually do not have to be nested within one another. That's very good. So to motivate this in real life, consider we have two models that we're competing against each other among a class of models. They could be nested within a larger space, but they don't have to be. And then each model has its own set of parameters, theta 1 and theta 2. So if you want to make this concrete, think of two regression models with different numbers of predictors, or two structural models with different paths going in different directions. Same outcome, but different directions. Now, the goal is to quantify, to create a quantity that expresses the extent to which the data support M1 over M2. And then one quantity could be the posterior odds. So, if you look at equation 6, this is the Bayes factor, in essence. If you look at the numerator, you're going to look at something that's going to look a lot like Bayes' theorem, with a twist. Posterior probability of model 1 given the data is equal to the probability of the data matter of time. So you have this posterior probability of model 1 given the data is equal to the probability of the data given model 1 times some prior probability for that model. That we have to talk about in a moment. Now I'm going to take that and I'm going to divide it by the same expression, but just for model 2. So one's my model and the other's your model. If you look at this term on the right-hand side, this thing here is the ratio of two likelihoods, called the likelihood ratio. But of a particular kind, it's the integrated likelihood ratio. And this term here is called the Bayes factor. That ratio right there is the Bayes factor. And so, but to get it to express posterior odds requires that we have some kind of prior probability that my model is to be preferred over your model before we see the data. So it may be the case that my model or your model is 3 times more likely to be correct than my model is, a priori. So we can actually set that up. Then we would have posterior odds, post-data odds, that your model is to be preferred over mine. Now, this weighting gives rise to an updated view of the evidence provided by the data for either hypothesis through those posterior odds. The problem is this expression right here. It may be difficult to believe that a priori that one person's model is better than another person's model to start with before ever collecting the data. So it may be the case that what you would rather do is assume that all of the models that you're going to be comparing have an equally likely probability of being the true model. There we go again with the true model. And that for this particular comparison, we're going to basically say the probability that this model is the true model is 0.5. And the probability that this model is the true model is 0.5. Therefore, these are going to become 1.0. And the Bayes factor, the posterior odds, is simply the integrated likelihood under equal prior odds, which is typically how it's computed. So in practice, there may be no preference for one model over another as being the true model. In this case, the prior odds are neutral. When the prior odds are equal to 1, then the posterior odds is the Bayes factor. And expressed in terms of odds, actually. Now, there's a long string of math that will get you from equation 6 to a very popular measure called the Bayesian information criteria, the BIC. This is used actually most productively in frequentist situations and not Bayesian situations, primarily because these prior odds go away. So all you're really looking at is integrated likelihoods. Not much Bayesian there, really. There's not much Bayesian there. So again, we can consider two models, M1 and M2, and let's just make it for simplicity now. M2 is nested in M1. And so this is the expression for the BIC. Now, what you need to read into this expression is simply that the BIC is another measure of fit and a measure of penalty. And these information criteria, such as the Bayesian information criteria or the Galecki's information criteria, or all of these, have basically this expression in common across all of these criteria. It's this that changes. And it's this little piece here that comes from the long math that gets you from the Bayes factor to the Bayesian information criteria, which I don't need to go into. But you're probably already familiar with the BIC. It's used for model comparisons. And the difference between two BIC measures, the BIC number in and of itself has no value whatsoever. It's just a number. But it's in comparison to other numbers that matter. And so you can take the difference between two BICs and look at those numbers and make model comparisons that way. And there have been some rules of thumb, because that's what we seem to have to do as a species, is have rules of thumb. So there are the rules of thumb that have been typically used. If you consider M1 as the reference model, then the model of which M2 is being compared, then this is the kind of information that you would get. There's the big difference, translated to a Bayes factor, and then the evidence against M2, and here are the words that you tend to see associated with that. Now, interestingly enough, the BIC is ironically not fundamentally Bayesian, though it's called the Bayesian information criteria. And an explicitly Bayesian approach to model comparison has been developed based on the notion of Bayes deviance. And this has led to something called the deviance information criteria, which really is Bayesian, and which is what we're going to actually use in the JAGS program. Again, there's a similar idea. There's some measure of fit, and there's some complexity function here. But to make this Bayesian, we have to obtain the posterior mean over theta. So this is all done with respect to the posterior distribution. So we get a posterior mean, the posterior mean over theta, and then we're going to compare that to the mean of the posterior distribution. So it's the distribution of the posterior, the deviance of the posterior distribution minus the posterior distribution of the means. That's basically it. And that gives us the deviance information criteria, but it's used the same way as the BIC. As you're looking at alternative models, the model with the lowest deviance wins from the selection point of view. Yeah.
May I ask a question regarding the use of BIC? You were just alluding to the fact that the two models have to be, well, you didn't say they have to be, but my question is, do they have to be?
No, they do not have to be.
Exactly, because from the modeling approach, I could come up with any models I like, and then I just let the data speak,
That's it.
considering the prior
Yeah, that's
data
true.
I have. Right?
Yeah, yes. The BICs and none of these have to be nested models, which makes them powerful in that case. So the DIC is obtained by calculating this equation over the MCMC samples, and the model with the lowest DIC is preferred. So let's get now to the second example, which is with multiple regression, which brings all these ideas in. This was an example. This is a toy example because I'm not really taking the nuances of the Pearls data set that seriously. It is Pearls data. This is the Progress on Reading Literacy study out of the IEA. And I'm going to have some reading scores on these students. It's going to be Canadian data. X is going to be a measure, a matrix of background and attitude measures, predictors. And I assume the normal linear model relationship.
That's one more question.
Mm-hmm.
Why do we assess the model fit or compare the models based on replicated data? Like in machine learning now, they use this testing sample and learning sample or training sample and testing. Can you do the same?
Yes. Yes, you
Would it be
can.
more accurate way to assess the model when you bring the new data unrelated to?
Well, yes, that's a cross-validation, is what you're talking about. And the answer is, of course, you could do that, and you would want to do that. In the absence of cross-validation, you just want to see whether or not your model. This would be like likelihood ratio chi-square statistic testing, where you're just looking to see whether the model fits, the model covariance structure fits the actual covariance matrix. But if you had the opportunity to run this analysis again or split the sample, that would certainly be preferred. And in fact, I will talk about Bayesian model averaging because in some work that we've done on this, that's exactly what you do. But yeah. So I'm going to write the normal linear model. And what's important here is all of the usual regression assumptions still apply. They all still apply. You can't have collinear x's. You're going to probably make an assumption about the disturbance term being normally distributed, especially if this is normally distributed. If the data are actually following a nonlinear model and you're specifying a linear model, you've made a mistake. And that's going to show up in the Bayes results just like it would show up anywhere else. So we're going to assume that the Pearls reading scores are, there's a typo here, Pearls reading scores are generated from a normal distribution. That's not unreasonable for this data, actually. You'll see this later, but again, this is just because you're going to keep these slides. In case you want to go back, this is what you can see. Here are the variables that I'm looking at. I have a gender variable, one is male. I have some measure of the number of books at the home, some school climate variable about the amount of bullying and teasing in the school, some measure of the student's motivation to read, their confidence in their reading, then some perceptions of whether the teacher's easy to understand in her teaching or his teaching. The student interested in what the teacher has to say? Does the teacher give the student interesting things to read? So it's a kind of a EdSci kind of statistical analysis. Now, I will go again to, where was I before? Now I will go to the multiple regression package, and I'll go to model 1. The basic setup is the same. Difference is now I've read in some data. I have to do a recode here because Perls doesn't code. It codes sex 1 and 2, not 1 and 0. I am going to just do some R programming here to read in the data that I want. Canada's participation in Perls is an immensely large sample size, so I'm just cutting this down because when I ran this, I needed to, get home and see my family and all these other kinds of things. So I just cut the sample size down quite a bit. I'm not going to do anything fancy with missing data, so I'm just using list-wise deletion, which of course is never recommended, but I'm just doing that for the simplicity of this. Here is your JAGS code again. So I brought in R, I brought in the data in R, and I did my manipulations. Now I'm about to go to JAGS. Start off the same thing with model string. And now I'm going to write my regression model, because my regression model is, in fact, my likelihood. So for I equals 1 to n data, I am generating the reading score. I'm assuming the reading score for person I follows a normal distribution with a mean mu sub I and precision tau. The mean mu sub I is now modeled as a function of these covariates for each individual. Okay? Now, in this, here's where it gets a little bit more complicated than what we had in the previous slide. In this little section right here, I'm going to obtain the information I'm going to need for the posterior predictive checking that I'm going to do. In particular, I'm going to examine the distribution of the residuals to see whether or not they are distributed nicely across the regression line. So that's the posterior check that I'm using in regression to establish whether the regression model is reasonably accurate for the data. A perfectly reasonable thing to do. So the first thing I'm going to do is I am going to generate the actual residuals from the data itself and from the model for the data. So that gives me the residuals. Then I'm going to create a new set of residuals that are random samples from that model, from the iterations, and new sets of residuals from each of those iterations. And that's what the comparison is going to be. Then I'm going to put priors on all of my model parameters. It's probably a more elegant way to do this, but I want you to see every step of this to the best of my ability. So I need a prior on the intercept, all of the parameters, including the precision. And actually, for this particular case, what I want you to do is ignore this because I don't actually call it later. So just don't worry about that line. So this model is a model for non-informative, basically quite vague, prior distributions for all of my model parameters. So this isn't pretending like I don't know very much. I prepare the sample for coda processing, just like I did before, only I have more in here, is basically it. I'm going to get some summary statistics, which are not really that important to look at right now, but I'm going to list out the variables, list out the parameters. But in order for this MCMC algorithm to actually also calculate these fit statistics, they are part of the algorithm as well, and so they have to be called in as parameters themselves. And it's going to look weird in the output, but it's there. It's just, you need to do this in order for this algorithm to actually calculate those residuals. Then I'm going to run my number of iterations, the same thing I had before, adaptation steps. I'm going to look at 50,000 post-burn-in iterations this time. Kind of a better starting seed, 5,000 burn-in. And now, within CODA, I can calculate the deviance information criteria. It's going to obtain, out of those 50,000, it's going to use 5,000 of those samples to calculate the deviance information criteria. And in fact, I then ask for it, and there's the number you want to pay attention to when we go to the next output. 39699. That is the deviance statistic. It's kind of like a BIC, but it's not a BIC. It's 39699 is a number that we would use to compare to some other number for model selection. And here we go. That's not good. That plot's not good. That's suggesting there is some clear problem in attempting to estimate the posterior distribution of the intercept. Now, it's not terribly surprising. I set the mean of the intercept to 0. But the mean reading score in the population of the Pearl sample is something like 400, 300, something like that. It's way, way off. But it's pedagogically useful to see what a bad trace plot looks like. And that's a bad trace plot. Beta 1, beta 2, beta 3, kind of look, sort of lumpy, does not look good. These would give me some pause for concern, I should say. This is not that good. Beta 4, beta 5, beta 6, these are all kind of not really showing. I mean, ultimately it's going to be okay. All the information is going to say it's probably okay. I myself would be a little bit concerned about this, and it doesn't surprise me too much. My priors are fairly far off. I mean, I know this now, but this would be something that you would begin to see. So this is an example of a set of trace plots and posterior density plots that really don't look quite like the way you would really want them to look if you had true, really good convergence to the posterior distribution. These two ones, fit and fit doc, nearly just ignore them. The precision, the same. Not great. Not great. And by the way, this is just regression analysis. This is a relatively simple model. And you can see where convergence becomes a very difficult thing to really establish.
Hold on a second, please. You didn't make your priors very strong. So why is this being picked up in the trace plots? Shouldn't the data...
They're far off. It's not just the precision that's wrong. The means are wrong.
And that's being picked up here.
Mm-hmm. Yeah, that's what I think.
It's not that the data because the data are strong in comparison to a relatively weak or weakly informative prior, that they can overwrite.
No, because, so this is a good example of a situation. I'm not 100% sure I know what the reason is here. Remember, this could also be that this is not a really great model for the data. Or there could be some collinearity in here. But I will say this. The sample size for this study was what, 5,000? Right? And here's an example of non-informative priors with a sample size of 5,000 where I am not seeing really great convergence. Right? So this issue about how big is really, it's not a question. It's really a question of convergence. Right? And you have to still compare this to another model. So a sensitivity test would be required as well. But the first thing I would do is I would try to stabilize this convergence, because you're from a practical point of view, unless all of these things look like they've converged well, you can't go on. You can't say, I won't interpret the intercept when everything else looks okay and the intercept looks bad. You have to have convergence across all the parameters in the model. Yeah.
So I guess the way potentially to massage data in this kind of analysis is to try to find priors who will facilitate the convergence, right?
Yeah.
And then when you submit your paper for publication, I guess the key will be for reviewers to push your, why do you have these priors?
Exactly. And
this is where people, instead of massaging the significance level, you start
with two exceptions. With two exceptions. One's probably, you're not going to like this. One exception is that you typically don't know if somebody's been playing around with their p-values. Here, it'd be very hard to avoid not saying this. Explicitly saying it. Second, because you have to make your priors explicit, someone's going to have to find out what your priors were. The second thing is, I would never do this without a sensitivity test. In other words, if I had to get priors to make this work, I would then want to check to see whether or not minor changes in those priors are causing vast changes in the results.
That would be a problem as well.
Yes. Yeah, oh, definitely. Definitely. Then, if you have tremendous sensitivity to priors, this could be the result of a sample size issue. Not here so much, but elsewhere. Let's look at the ACF plots. Now, these ACF plots, again, the plotting structure within the screen itself is not all that great, but you get the idea here. You will notice a couple things. First of all, they're not as clean and beautiful as they were in that previous example, but they are going down. And that's the key. The autocorrelation function plot is, in fact, going down. So this suggests the possibility that maybe some of the problem in the algorithm that's led to those trace plots is not enough burn-in and not enough post-burn-in iterations. I might add many more burn-in iterations and many, many more post-burn-in iterations. That what we could be seeing here is that this thing got trapped, as I said earlier, trapped within a part of the posterior distribution, at least beyond the post-burn-in, that's causing this kind of thing. Again, it's a little bit speculative, but you would have to think it through this way because the convergence is everything. You cannot go on unless this thing is converged, but we are anyway. However, with regard to the chains, there doesn't seem to be any evidence that the chains are problematic here with the Gelman plot. They're maybe both not that great, but they're at least pretty much tracking each other. And finally, if we take a look at the Galecki Diagnostic that we mentioned before, you can see a couple of parameters here, not many of them, that are not satisfying the Galecki Diagnostic. All in all, I'm not going to do that, but all in all, I would stop. I really wouldn't go on. And I would check my priors, which are completely off in this case, to a great extent. I would check my priors, I would check the model, I would do all the usual regression diagnostics to make sure there's nothing like collinear data or other kinds of problems of that sort, and add some burn-in, more burn-in to it and more post-burn-in to it to see if I can get it to stabilize, which I didn't do for this discussion, but anyway. Oh, by the way, those are the actual Gelman values, which look fantastic for everything we want to go, so that's okay. So an inspection of the convergence plot suggests overall okay, but I think it's problematic, and so I would probably stop. But if I weren't to stop, this is what I would get. Here are the results. Again, I want you to completely ignore those two lines. They're meaningless. They're just numbers that are being spit out. If one were to go on, these are the regression coefficients under the column mean. Those are the posterior estimates of the regression relationships, and you would interpret them just like regression coefficients. But they're just accounting for your uncertainty as expressed in those priors that you had in the previous analysis. And here is the 95% credible intervals. Again, the same exact thing. You can see some real discrepancies between the naive standard error and the time series standard error for many of these parameters, and that's reflected in the Acf plots that are not quite going down. Okay, now, here are the lines that give you the posterior predictive check on the residuals, the Bayesian p-value as well, and then a plot. And there's the plot. Now, this plot's really kind of interesting because if you are familiar with regression analysis, you know that these residual scatter plots give you a lot of interesting information. It tells you not only whether or not the scatter plot is above or below, basically randomly distributed across a particular line, but it also tells you about heteroscedasticity in the data. So when I take a look at this residual scatter plot, yes, my Bayesian posterior predictive check is 0.5, right on the money. But look at the plot. So now I have to go and start to think more carefully, not about my priors, although I probably should, but about the regression analysis as well. There's a violation here. There's something wrong with the residuals. It could be the priors, but it could also be that there's something about this regression analysis that needs to be looked at, a serious misspecification someplace. So don't forget that the Bayesian framework has a likelihood and priors. So your model is there, and everything about the model is there, and everything that could be possibly wrong just about the model itself is still playing a part. If it's misspecified, if it's the wrong model for the data, all of these different things that you've learned about in regression analysis doesn't get thrown out the windows just because you just became a Bayesian, at least for the next hour. Rather, what you have to keep in mind that this is a key part of the whole thing. Things have gotten harder. They have not gotten easier. But the idea behind the Bayesian sort of movement, if you will, is that what you get out of this at the end is much, much more intuitive than what you would start with. It's just more to it in terms of guaranteeing that the results that you're getting make sense. Yeah.
I'd like to ask about this because right now I'm working with these models that are called heteroscedastic linear regression models, where you model both the mean and the residual variance. And it's very useful, for example, sociology and inequality. It's not only about the mean, the difference between the means, but also how much uncertainty in your income you're exposed to.
Yeah.
So pretty much in this conventional framework, people decided we need to not purge heterogeneity system, but to model it.
Yeah.
But now I'm thinking about your approach, Bayesian approach. It seems like it does that as well, in the sense that you model now the variance in your coefficients, right? Does it ring a bell at all, or you did not?
It doesn't. This is how I would respond to that. I myself have not done that, but I don't see why you couldn't. In other words, if you have a regression model that specifically is modeling heteroscedasticity, so you have a parameter for that in the model, from a Bayesian point of view, there'd be no reason why you can't do that. You would just have to have a prior on that parameter. That whatever you think would make actual sense as a prior. As you I'm sure know, Bayesian statistics is not like a new set of statistics. It's the old set of statistics with priors. So everything you can do in a real classical sense, right down to the t-test, can be done in a Bayesian context. I'm not kidding. Can be done in a Bayesian context. You just need a prior on the treatment effect.
And when you don't have priors, like in this case, for example, very weak priors,
very weak.
Essentially going back to if they're very defined.
And I would actually believe that if I saw, I would be more inclined to believe this if I had better convergence criteria. I'm not convinced yet that there's something else that's not wrong. If I could solve that problem and I had this, then I clearly have heteroscedasticity, because now I'm back to sort of likelihood-based statistics. The priors aren't mattering very much. Right? The issue about the priors and the sample size, I think, makes great intuitive sense to me. If you think about priors as information, and if you think about individuals as information, then the idea is if you have an infinite amount of information in terms of having an infinitely large sample, then you don't need your priors anymore, because you truly have all the information. Each individual's observation is a bit of information. You have all the information. So no amount of priors would ever move that. But on the other hand, if you don't have very much information in the form of sample size, then your priors would have to begin to dominate. On the other hand, on the third hand, if you had very little in the way of observations and very little in the way of priors, meaning non-informative priors, then you have very little of anything. And so if that's the case, then what you have to expect is that your posterior intervals are going to be very, very wide. Now, that's a hard sell for people unless you start thinking about this notion of like the accumulation of evidence. Of course your posterior intervals should be very wide. You don't have any sample size and you don't have any prior information. So you don't have anything. And if you don't have anything, then anybody's guess is as good as anybody else's guess as to what the outcome of something should be. So for me, philosophically, it makes absolute sense. So but because we're in this computationally intensive framework, it seems to me that if I can conclude that everything is converged beautifully, and I have a large sample size and my priors don't matter, I am back to regular regression, and this is a problem. So I'm completely with you. So you can draw the plot this way, or you can draw the plot this way to look at the residual differences around 0, if that's more convenient, but they give you the same basic information. Okay, now if we go back to, oh, sorry.
Going back to the summary table. If I remember correctly, at least in OpenBugs or so, you also get the mode, right? Instead of, or in addition to the mean.
That's possibly true. This one just seems to give the mean. I don't know if you can ask JAGS for the mode. It's possible.
Okay. Do you have any preference, mode versus mean?
I don't personally know, and usually they're not going to be very much different from each other if the sample size is large. But
so you would also always report mean.
I've seen both reported, but I don't know if you can get the mode out of this. It's possible. I don't know why you couldn't. In fact, if JAGS will give you actually all the numbers anyway, you can calculate it yourself. But now what I want to do is, if you remember back again to the this value 39699, what I want to do now is make a comparison between that model and this one with informative priors. So this is going to be exactly the same setup. Exactly the same setup, except I've now put informative priors on the regression coefficients, but I've left the precision non-informative. These priors, well, quite frankly, I cheated a little bit. I just sort of looked at a frequentist regression analysis and rounded around a little bit. Not really fair. don't do that. Don't do that. It's sort of like empirical Bayes, and it's not really a good thing to do. So what I want to do now is, I'm not going to take you through all of the details of the processing because it's exactly the same. The only thing in the output that's changed, or in the input I should say, that's changed is this. The reason why I'm keeping the precision non-informative is, well, for several reasons. But the biggest reason is that the precision term in this particular analysis represents basically the residual term in the regression analysis expressed as a precision. Since the disturbance term in a regression constitutes everything you don't know, then how could you put an informative prior on that? I think it would be really hard to do. So the tendency you'll see is to keep the precision terms of regression equations non-informative. And the non-informative one I'm using is the gamma coefficient, the gamma distribution, and I'm making it relatively non-informative. So go through, and there is the deviance. Now this is interesting. This deviance is higher, not by a lot, but by enough, suggesting that all other things being equal, and they're not, by the way, because that model didn't converge all that well, but all things being equal, the model with the non-informative prior shows better posterior predictive fit than the model with informative priors here, even though they're much, much closer. A little bit better trace plots, not much, a little bit better. A little bit better ACF plot, especially for the intercept. So the intercept, I was able to improve by getting much, much closer to what the actual mean reading score was. Everything else looks exactly the same. The Galecki Diagnostic, again, forget these two here, that's not important. The Galecki Diagnostic is okay, but not great for one of these parameters. It wasn't the same as the other one we saw before. This is the same. So let's see, results, B1, 1.705. 1.74, 11.40, 11.04, 7566, 5375, that's sensitive, -4, -2. Some of these parameters are not showing much of a difference depending on the nature of the prior. Some of them are, which means that those priors may be wrong for that parameter. Too high a precision perhaps around for something that's a little bit wrong, plus a large sample size associated with that. Hard to tell. Let's take a look at the posterior predictive check. No difference. The residuals are roughly distributed across the line, but there's still some evidence of heteroscedasticity, though I think maybe not as bad. No, it's not good. But anyway, that's the exercise through these two. From a model choice point of view, the model with the non-informative priors would be chosen as being a better model from the DIC point of view. However, both models are showing some convergence problems, in particular the non-informative model. So I'm not entirely sure that this is the best example, but it's a real-life example, so it's good from that point of view. Let's go on. Now, what we just did a moment ago is we had two models. A model with non-informative priors, model with informative priors. We could have changed variables in and out of the models and so on and so forth. But ultimately, we would select one and then act as though that was the model that generated the data. And we act that way because that's the one we're actually drawing our conclusions with and making policy recommendations on and so on. So we are acting as though that was the model that generated the data. So as I mentioned in the previous lecture, that there is model uncertainty. in the sense that there are a large set of possible models that one could have chosen, and to select one of them ignores this uncertainty, and that Bayesian model averaging is a way to go on this. So let me now get into more detail on BMA and then show you what the results of the BMA looks like. So we're going to think about some quantity we're interested in, and we'll call that quantity, we'll think of that quantity as a future observation. So what I'm interested in is prediction. I'm interested in predicting the future, a forecast, if you will. And I'm going to note that quantity by the Greek letter upsilon. I chose upsilon because upsilon is an underrepresented Greek letter in statistics, and I thought it needed its 15 minutes of fame. So now, imagine we have a bunch of competing models. So you have a model and you have a model. And these don't have to be nested, but for simplicity, just imagine a regression model with different regressors in it. Same outcome, but lots of different regressors. And what I'm interested in is the posterior distribution, of course, of this future observation given the data. And I'm going to write it this way. I'm going to go from right to left again. This thing here is called the posterior model probability for model K. Remember, I have lots of these models. And this is the posterior model probability, which I'll define in a moment. I'm going to multiply that posterior model probability by the probability of that future observation predicted by that model, but I'm going to sum over all of the models. So this is a weighted average, weighted by the posterior model probability to get the probability of the future observation given the data. So what is this? This is a mixture of distributions. It's a mixture of distributions with mixture weights defined by each model's sort of likelihood or quality. Now, this posterior model probability now starts to get to look like Bayes' theorem a little bit. Posterior model probability for model K is equal to the probability of the data given that model, there's your likelihood, basically, times, well, we saw that before, there's the prior probability for model K. Then we divide by this thing here so that this is a nice probability distribution. It goes to 1.0. Now, what you can imagine now is if we all have different competing models, so the same outcome but different variables, we can imagine that all of our models are going to have slightly different posterior model probabilities, reflecting that your model may be better than mine in some sense, post data, the probability. So what you're doing here is you're saying, look, I have a prior on the model that says that my model is, has a 0.5 probability of being correct. Then I confront the data with my model, then I have a posterior model probability. That's basically post-data model probability, right? So each one of our post-data model probabilities are probably going to be different from each other because our models are different from each other. So that's what that is. This thing here, we already saw this before. This is the integrated likelihood, and here is where it gets interesting because this integrated likelihood is the probability of the data given that model, which says that for each model, K, there's also priors for that model, K. Because if our variables are different for different models, our priors might be different as well. So things get very complicated here, really complicated. But what we're doing is we're combining models. We're doing model combination. We're not choosing a model, we're combining across models. And what we know, going back quite a ways now, is that Bayesian model averaging provides better predictive performance than any single sub-model based on something called a log score rule. Meaning, if you look at, say, predictive coverage, or the log of predictive coverage, the log score rule, BMA will outperform any single model, unless you happen to have the true model. Right? Then the true model will outperform. But in the absence of that, BMA always wins. It always wins. But as you can imagine, perhaps you're thinking this, BMA is very difficult to implement. In particular, you're going to have a large number of terms here. There's going to be integrals that are going to be hard to compute. It's difficult to elicit what the probability of my model is pre-data compared to the probability of your model. So instead, what we might use is a flat prior and just say the prior is a 1 over the number of models is used as a prior. And what that means is every model is equally likely to be preferred by the data. That just puts every model on an even playing field before that individual model is confronted by the data. So the software that does Bayesian model averaging uses that as a prior for what we call the model space, the space of possible models. By the way, it also puts a non-informative prior on all those parameters of all those models as well. This is not so much of a problem for us because our models tend to be simple linear models, and we tend not to compare simple linear models to very complex nonlinear models. But in fields such as weather forecasting, you have very different physical models, and trying to average over those tends to be a rather challenging aspect of it. But what we tend to do is to reduce the number of models that we have to average over. We incorporate algorithms that search, they're kind of machine learning algorithms actually, that search the model space and reduce the model space. So imagine I have a regression analysis with 10 predictors. Then the fact is I have 2 to the 10th possible models in this space. That's a pretty big number. And so rather than traversing the entire model space, what I'm going to do is come up with a set of principles that are going to include some models and exclude others. And those are based on the notion of Occam's window and Occam's razor. And so you can quantify this. And if you think about the window as a window, what you're basically doing is you're opening and closing the window according to certain criteria that you can choose so that some models are in and other models are out. The models that are out make virtually no difference compared to the models that are in according to this criteria, and then you've reduced the model space rather dramatically. Another approach is called M3, or MC3, that's a typo. Markov Chain Monte Carlo Model Composition is the name of another algorithm, and there are others. So let's look at BMA. What does a BMA output look like? All right, so what I'm going to do is I'm going to use a program in R. This is not JAGS. A program in R, cleverly referred to as BMA. And I am going to look at my simple little regression analysis with Pearl's data. And what I have to do is I have to tell the BMA program to select the dependent variable and the independent variables, if you will, to run the BMA. And so the dependent variable in my file Canada BMA is in the first column. That's the reading variable. And then the X's are in columns 2 through 9 of my data set. And then I'm going to run a program within the BMA package called BICReg. I'll tell you what that is in a second, and then I'm going to summarize it. One of the things that's very complicated about Bayesian model averaging is this integrated likelihood ratio, especially when you're doing this across lots and lots of models. So what Madigan and Raftery and other colleagues have figured out is how to do something called a Laplace approximation to the Bayesian information criteria, which can be used to solve very complicated integrals. So instead of doing MCMC, there's an approximation to this, which is extremely fast. When you're done doing Bayesian model averaging, this is what you get. So what I want you to do is focus your attention on models 1, 2, 3, and then it wraps over here to 4 and 5. Via Occam's window, 5 models were retained. Out of the 2 to the, I think there's 9 variables there, 2 to the 8 or 9, whatever, what's it? 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8th possible variables, still a pretty big number. 5 are chosen of this. What you're seeing here is model 1. Model 1, notice, has this variable sex that's not in that model. And if you go down, these 2 variables, I don't recall exactly which ones they were, but I can go back. They're not in the model of that model choice. Oh, I see. All right. You get an R squared. It's probably a naive R squared of some sort. You get a Bayesian information criteria, and there is the posterior model probability. The output arranges these things from the lowest BIC to the highest BIC. And so if you were playing the game simply from the standpoint of the BIC, you would choose model 1. Model 1 has the lowest BIC. Its posterior model probability, though, is quite a bit less than 0.5, indicating extraordinary model uncertainty. If you were to choose this model, from a posterior model point of view, it's not a very good model at all. But it's got the lowest BIC. Now here's the interesting thing about it. If you look at the BICs for all 5 of these models, they're almost not different from each other. Meaning that, in fact, from a BIC point of view, from a model selection point of view, these models look equally good. But from a posterior model probability point of view, these models are all really bad. Now, as it turns out, if you sum these model probabilities up, they sum to 1.0. In other words, the entire model probability space is 1.0, accounted for by these 5 models. But any given model here actually has a post-data probability that's really quite poor. From a prediction point of view, if you were to go on now and use model 1 on the basis of the BIC for prediction, you'd certainly get predicted values. But they would not be as good as if you took a weighted average of all these coefficients that appear in these models, weighted by their posterior model probabilities. And that's what this column shows. EV stands for expected value. And what these are weighted averages of each of the coefficients when they appear, weighted by their posterior model probabilities. If you now use this column if you now use the EV column to do your predictions with, by holding out half the data, using one as a testing set and the other as a validation set, you will do better, in a frequentist sense of the word, you will do better using Bayesian model averaging in terms of predictive coverage than any of these single submodels that you could have chosen. Now, just to show you how interesting this actually is, let's take a look at the male effect. This is the male-female difference. I don't know if from a frequentist point of view, I have no idea if it's statistically significant, and I don't care. Notice that they're roughly the same value, 4.599, 4.925. It doesn't appear in these 2 models, it's just here. So you would conclude, if you looked at model 2 or model 3, that there's about a 4, almost 5-point difference, whatever that means, between males and females on this. Look at its expected value when averaged with respect to the model probabilities that it appears in. 2.388. So it begs an interesting question. This gender effect, such as it is appearing in a model that has very poor post-data probability associated with it. But when accounting for the uncertainty in the models in which the gender effect appears, the gender effect is not as big as you would have concluded had you chosen one of these models, which you might well have done because these BICs are not different from each other. You might have, for completely substantive purposes, said, you know something? I can't tell the difference between these 2 models. I'm going to choose this model. Our squares are almost the same. I'll just choose that model. I don't know why I would do that, but I might do that. Your conclusion regarding the gender effect here, and this appears in other coefficients as well, would not be the same as if you took into account model uncertainty in addition to the parameter uncertainty that we're taking into account. The BMA will also give you these posterior plots, which have to be taken a little bit carefully. Basically, what they're saying is the thing that we mentioned before. You can read off of this plot the probability that the effect of gender, in this case, is greater than 0, or not equal to 0. So this is that column here. Probability that the male effect is not equal to 0 is about 50%. 51%. It's a strange plot, but nevertheless, you can read off of this. You know, you don't see a black line here. That's because this thing is so far off to the other side. The non-zero part of the distribution is scaled so that the maximum height is equal to the probability that the coefficient is not zero.
So how is it calculated that probability the coefficient is not zero? Because in a distribution it's
Continuous.
1 point.
Yeah, right.
So how
Yeah, that's a very good point. This is why this is deceptive. It's deceptive. I'm not entirely sure I like this. It gives you the sense that if this is the probability that the effect is not zero, then 1 minus this is the probability that it is zero, but it can't be. The probability that this thing is zero is zero.
Yeah, exactly.
And so you've got to be careful about how you interpret this thing, and I probably wouldn't. I'd be more inclined to, try to read off the probability distributions differently, but yeah. So that's BMA. And my research group has been looking at BMA now for a few years in other applications that we've been interested in that I would love to discuss with people here at some point. And I guess you guys got to go pretty soon, right? Where are we in time? Does this end at 4?
That was the rough estimate. Some people are already.
Oh, okay. Well, let me see if there's, the only thing I would wrap up is that what I have in here, you guys can keep it because now you get the basic idea, is I have these setups for hierarchical linear modeling, HLM, basically, and I have a setup for factor analysis. Now that you've seen how the JAGS program is basically set up, you would have it won't be much of a problem to figure out what's going on. I will point out one thing very quickly. In terms of multi-level analysis, the situation's a little more complicated because what you have to do is model not only the likelihood for individuals within schools, let's say, but then you have to model the differences between schools. So the likelihood, again, is your regression equation. Whatever that happens to be has to be modeled up here. The priors, in setting the priors up, again, it's going to be a little bit more complicated because you have many, many more parameters in a multi-level model. And in particular, last thing I want to say is that your variance terms are really tricky because you have, if you know what HLM is or are familiar with hierarchical linear modeling, you have variance terms at different levels of the system. And those variance terms at higher levels of the system become very, very hard to converge. So lots of people, have been working on trying to find good weakly informative priors for the distributions of the variance terms, particularly at level 2, which is why I wanted to show you this, so show you what a really bad looking output looks like, so that you're not surprised by it if you ever actually try to run this. It's not that simple in multi-level models. From a Bayesian point of view, these are considered complicated. So you'd have to just be very careful, especially about variance terms at the upper levels of the system. I guess there's like 2 more minutes or something like that. And you guys can. I won't start anything new. So if you have any questions about this,
I have 2 more
yes, sir.
It's very basic. Like you always have like made up priors now.
I'm sorry.
Your priors you used were basically made up by you.
Yeah,
right
they were.
So what would be a good prior, and where did you get it?
So that's a great question. I'll answer it quickly because I know you guys are off to running. The question you're asking is sort of generically referred to as the elicitation problem, which is how do you elicit priors? And priors can come from lots of different sources. They should not come from the same data on which you're running the model. That's a different problem. But they could come from expert opinion. They can come from previous data. A good example of this, and why you also have to be careful about this, is something like PISA. So PISA, as you may or may not know, has many, many cycles that have gone back since the year 2000. It's like on its 6th or 7th cycle right now. So you might take a current cycle of PISA within the United States, for example, the reading cycle, and you might say, I'm going to analyze that data, but I'll use the previous reading cycle of PISA to get my priors. That's perfectly legitimate. It's the same exact data set, different people. So there's nothing wrong with that. But you're making a much greater substantive judgment when you're doing that. You're saying that in the United States, in the time between the last reading cycle and the current reading cycle of PISA, nothing at a population level has really quite changed. And so that makes for good priors, but I'll check them with experts as well. and see whether I can get a good sense of what those priors should be. Now take the situation of Germany using PISA 2000 versus, which was reading, by the way, versus a later cycle, the 2009 cycle of PISA in reading. You might say, I can use PISA 2000 data in Germany for PISA 2009, and that may make sense. But there, I think you would have to have a little bit of a deeper conversation about whether PISA 2000 makes sense for PISA 2009, because something happened after PISA 2000 in Germany, right? And to the extent that that may have changed the system exogenously, so that that just doesn't make sense to use as a prior anymore, you would want to bring in additional data, additional experts to try to get a sense of what works. That's the hard part of it. And that's why I think a lot of people just use default non-informative priors wrongly. So they're not taking the time to see if they actually can put in some knowledge into those priors.
You have to bring it to the scale of your instrument.
Yeah. Yeah, you also have to think about that. Like, what is the scale of the instrument you're using? And remember, these are priors on regression coefficients. So as you're thinking about the relationship between y and x, they're in a scale, right? And so you then have to think, well, what would that scale look like, and what would the precision around that scale look like? So there's a great deal of thought that needs to be given to incorporating that information. Yeah. It was never meant to be necessarily easy or some sort of an easy improvement. But I would still argue that the intuitions that come from it are much, much nicer than the intuitions that come from frequentist statistics, I think.
Maybe that's why they doesn't get popular, because it's very hard
It's very hard.
to find the priors, and so then how do you
Mm-hmm.
publish?
Yeah, I mean, we were mentioning that before. You're just the whole dialogue would have to change. I think it would.
What it means to have theory, what it means
Yeah.
to have
Priors.
contribution.
Mm-hmm. Yeah.
To ask you something else about coefficients. You specify the priors in terms of mean and variance.
Mm-hmm.
But what about the distributions themselves that you assume?
Right.
Gamma versus
Right.
gamma versus-
So this is not a good one to look at, but if you look at this one, for example, where I'm putting the priors in here, this is a very good question. So notice that, forget the fact that this is non-informative. Notice that for the regression coefficients, I've specified normal distributions. That's because we know something. The asymptotic distribution of a regression coefficient is normal. So we're taking into account the fact that what we have is what's called a conjugate prior. We know what the distributions of regression coefficients should be in a frequentist sense. So why throw that information out? That makes for a good conjugate prior. However, here, when you're looking at precisions, the gamma distribution is the conjugate prior, but it's not the only prior we could have used. If we're talking about variances, what do we know? We know that variance can't be negative. So this is going to be positive, let's say 0 to some number, and it might look like this. Actually, it won't look like that. It will look more like, well, maybe like that. Or it'll look like this. That's got a name. That's called the half-T distribution, or the half-Cauchy distribution. So it turns out that we can specify, and this is what people are doing to try to find ways to get around the problems with higher level variance terms for HLM, is to try to figure out what are some sensible priors for these precisions, because that's where it actually gets hard. But to really move deeply into Bayesian statistics means you're going to have to learn, one's going to have to learn about distributions you might not have learned about before.
So you make your judgment, expert judgment, if it's this and that, and then you use something which approximates.
Yeah, basically that's correct. Or there's certain things you know. For example, a binomial distribution. So any good statistics book is Bayesian statistics book is going to have all this stuff. A binomial distribution has a parameter p, let's say. That p is a percentage. It's the proportion, right? The proportion has a distribution. It's called the beta distribution. So now, if you're going to model some sort of binomial process, and you want to model the parameter prior has to be a beta distribution, because that's conjugate. So now suddenly you're getting into, let's say you want to look at multinomial data, multinomial data has thresholds. There's a distribution for those thresholds. It's called the Dirichlet distribution. Ever heard of that one? I'm not even sure I'm pronouncing it correctly.
Now in this
Dirichlet.
machine learning.
It's a multivariate beta distribution. So suddenly there are all these distributions that you may never ever had to have to deal with. I certainly didn't, and I certainly never learned them until you start getting into this, and then you realize, well, to do this correctly, you have to understand what the distributions of parameters of distributions are. Right? The normal has a mean, the mean's normal. Binomial has a proportion, proportion's beta. Poisson has a lambda distribution, lambda's gamma distributed.
You can go farther into the nth moment if you want.
You could. That's getting harder. Yeah, sorry. They've all left.
I've got an online participant who's
Oh,
got a question.
okay.
Can I ask this question? I'm running a linear regression. My dependent variable is 0 to 10 and skewed towards 0. After I run my model, the posterior predictive checks show that now the Y-rep has a normal distribution. Does that mean that my model is wrong?
What has a normal distribution?
The Y-rep?
Oh, Y-rep has a normal distribution.
Y-rep.
Y-rep is normal? I don't know. I don't know. So they must have plotted the Y-reps. Well, I guess the question is, how did they model the parameter? How do they model the parameters? If they model the parameters as normal, like normal priors, then I think that maybe that would not be surprising. But if they had modeled the skewed normal variable as a skewed normal distribution with the right priors on that, then maybe the Y-rep would not be normally distributed. The Y-rep is the distributions, not of the data. Well, it's the distributions of the data under those priors. I'm not sure.
She's listening, so.
Yeah, no, I'm not sure. I don't know if I would have to see sort of what the whole model setup is in order to check to see why the Y-rep would be normally distributed.
I have a sense that everybody is pretty impressed by what you had to say and exhausted.
Yeah.
So I think this is the right time to end this discussion. If anybody feels like he or she would like to ask David another question, I'm sure we can do this after we have cut the line and officially finished our talk. So anybody who has to leave right now, please go ahead. Thank you again, David, very much for this input.
Yeah, my pleasure. Thank you.